we present SymForce, an open-source library for fast symbolic computation, code generation, and nonlinear optimization for robotics. This is work from the Skydio autonomy team and was published at Robotics, Science and Systems in 2022. SymForce is made for writing algorithmic code for tasks like SLAM, MPC, calibration, bundle adjustment, and controls. Compared to alternatives, it results in faster runtime performance, faster development cycles, and fewer lines of code to maintain, sometimes by an order of magnitude. SymForce powers tens of thousands of autonomous drones at Skydio. It is suitable for use in educational contexts, in academic research, and for production robotics. The primary workflow consists of 3 stages: symbolic math, code generation, and optimization. First, a problem is modeled in Python with the SymPy API, extended to include geometry types, camera models, and Lie group calculus. Second, symbolic functions are introspected to auto-generate highly performant runtime functions. And third, generated functions are used as factors in our tangent space optimizer. Let's walk through this with a simple example of a robot moving through a 2D plane. The robot has noisy measurements for its distance traveled and bearing to the known landmarks in the scene. To begin, we write a residual function to model each of the sensor measurements. These functions output symbolic expressions, which can be explored, analyzed, and manipulated for rapid development. The top function computes the residual for distance traveled, and the bottom for the bearing angle to a landmark. Next, we pass each function to the code generation class and tell it what language to generate, in this case C++. We get a generated C++ function with an equivalent API to the symbolic function. This function has no branches or memory allocation, and its only dependency is the eigenmatrix library. By changing one argument, we can generate an equivalent Python runtime function that depends only on NumPy. SymForce aims to support many target languages with a plugin system. With one more function call, we can automatically compute tangent space Jacobians or a Gauss-Newton linearization with respect to any of the function arguments. Finally, we can construct a factor graph from the generated residual functions and derivatives at each time step, create initial values, and invoke the optimizer from Python. And the same optimizer API is supported in C++ once the user is ready for production use. Here we see the problem being optimized. This overall workflow scales well to a wide range of complex problems, up to hundreds of thousands of operations. And SymForce's code generator is broadly useful even without the optimizer. As we saw, SymForce does not require any handwritten derivatives, which tend to be one of the most error-prone tasks in robotics. SymForce introduces a novel method to automatically compute tangent space Jacobians of functions that operate on Lie groups, like rotations and poses. All a user needs to do is to build a symbolic expression and call the Jacobian function, as shown here. As a reminder, Lie groups are manifolds where derivatives are computed in a local tangent plane. For example, SymForce stores a 3-dimensional rotation as a unit quaternion with 4 scalars, but does calculus in the space of a local angular velocity vector with 3 scalars, a compact representation of the space. Given a function that operates on a Lie group type, its Jacobian is written as a symbolic function of an infinitesimal perturbation of the tangent space, retracted onto the manifold. However, this expression is singular and requires computing a limit, which is difficult and slow. SymForce implements 2 novel methods for computing this quantity efficiently and without loss of generality. The 2 methods are summarized here. Please see the paper for details. SymForce also introduces a technique to avoid singularity points without introducing branching, using an infinitesimal variable epsilon. For example, this strategy can create a branchless expression for sin of x over x without a singularity at the origin. Handling this correctly is key for robust behavior. The largest advantage of SymForce is speed. SymForce generates highly performant code by operating on the fine-grained structure of a computational task to avoid unnecessary work. Symbolic functions are flattened into a chain of instructions that share all common subexpressions, leverage sparsity, and avoid branching. Let's take as an example computing the product of x and y, the matrices shown here. Similar tasks are common when dealing with 3D transformations or applying the chain rule during automatic differentiation. Naively computing x, y, and their dense product requires 417 scalar operations. SymForce's generated expression, as shown here, requires only 34 operations. SymForce generates output entries directly with no overhead because it knows the exact sparsity patterns from the symbolic code. In contrast, using sparse matrix multiplication at runtime is slow because it requires dynamic memory operations. In addition, SymForce is much more powerful at common subexpression elimination than a compiler because it can flatten and share terms across arbitrary symbolic function boundaries. We profile this task for a range of matrix sizes and sparsity patterns from the SweetSparse collection. SymForce outperforms the best of Eigen in C++, sparse or dense, by 4.8x on an Intel CPU and 7.1x on an NVIDIA Tegra CPU. Next, we measure the linearization time of a robot localization problem with 5 poses and 20 landmarks, implemented idiomatically in SymForce, GTSAM, Ceres, and JAX. We generate 2 SymForce formulations, a fixed size problem that is faster and a dynamic size problem that is more flexible. SymForce fixed size outperforms the best non-SymForce result, GTSAM, by about 5x on both Intel and Tegra platforms. SymForce Dynamic outperforms by about 2x. Please visit our repository or pip install to get started with SymForce. Thank you, and we look forward to your feedback and contributions.